Because threads can interact with the same data, and they can do this in orders that are not predictable to us, or maybe even at times that we would consider the same time, most code is not thread safe unless it is designed to be thread safe. This includes most of the built-in Java data structures. There are some which are explicitly designed to be thread safe, but most of them are not. So here's an example that uses an array list between two threads. Because it's shared memory, they're both allowed to access this array list, and it could be as many threads as we'd like. Even just two threads can cause this problem, but the more threads we have, the more likely it is we'll have this problem. So our runner extends thread, it just adds items to the array list. It's going to add 1,000 items per thread. And then we create a runThreads method that takes a number of threads, and we then create an array of all of those threads, and we tell them to start. And we wait till they finish. And we'll print out the size of the list at the end. The main method here, you can see, is just setting it to make 2 threads and do its job. We call the program once, and it creates an array list with 2,000 items in it with presumably no problems. We won't know the order that the numbers will get inserted there, much like we didn't know the order of our printing before, but those 2,000 items all got inserted. So if that's the only job we wanted to do, that works okay for several different calls to our list example program. And it works fine until it doesn't, until we get very unlucky and both threads go to call the add method at the same time. Here, the result that we see is an array index out of bounds exception. It may cause lots of different possible exceptions, and it may not always be obvious to us why that particular exception arose at that time. But this thread, or this error, is due to a synchronization issue. There's something in the ArrayList class that, for instance, maybe increases the size counter before it actually increases the space that's available for items. And so it may be the case that one of those threads asked to add something and got through the step of increasing the size counter, and then before it finished, the other thread asked to add something at a location that was past the current space available because it thought the size of the array list was bigger than it actually was in practice. They don't let each other finish doing the adding. And so we get that exception, and we've only made it through 1,162 items in that run before it happens. But then we see several other runs where the threads don't have any problems with each other, and it may take us several more runs before we hit an exception again. In this test, we'd had to do 29 successful runs before the first failure, but that's not predictable. It could be 29,000, could be 29 million. If we release a program, may see users complaining about the error immediately. We may see them complaining about it weeks down the line, months, however long before we hit that strange condition where multiple threads try to do the same thing at the same time or try to do things that conflict. This makes testing and debugging concurrent programs very difficult and means that the most important step in a multi-threaded program is designing it, and designing it to be thread safe so that our operations don't conflict with each other in this way, like increasing the stated size of an array list before you increase the actual available size of that array list. And you'll notice again that the error we get does not say that it was due to synchronization. It does not say that it was due to the two threads doing things. It just says there's an out of bounds exception. And so you may spend lots of time trying to debug this issue, thinking that the issue is about your index or your array tracking, your array size tracking and your index tracking, when it's not. It's about the threads interacting in a way that conflicts. So If we have two threads, T1 and T2, that share an object O that has this method M, then we can come up with an even simpler example where it becomes clear where the threading causes some conflicts and some issues here. So my method M returns a Boolean. It will return true or false. It should theoretically always return that X and Y are equal, because we say Y equals X, then we increase X by 1, then we increase Y by 1. But in a multi-threaded program, even with just two threads, if both threads call M around the same time, for instance, if T1 calls M and gets partway through, and then T2 calls M, then it may actually cause them to return false on this method. For example, if T1 calls and gets through doing its pluses, and then T2 calls before T1 hits the return and only increases X, and then for whatever reason, the exact timing is such that X has been increased by thread 2, but Y has not been increased by thread 2, and thread 1 chooses then to return, which we can't predict what order each thread will execute in, then it would return false. It would say that X is 1 higher than Y because Y didn't get increased yet in thread 2's call to it. But in a single-threaded program, we could always guarantee that X is equal to Y by the end of this method. There's no uncertainty about it. We can handle this in one way by stating that our method is synchronized. This means that only one thread can be inside this method at a time. So if thread 1 calls M, and then thread 2 needs to call M, it will have to wait until thread 1 is finished with M before thread 2 can even start with M. This will cause sort of pauses in our program where some threads have to wait on something that is synchronized, but it will ensure that you never halfway finish a method before some other thread calls it. So this gives us the ability to interleave and run on multiple cores those different threads and handle our M calls, but it ensures that we always finish one M call before we call to another instance of M, before we call M in a different thread. Another way to handle this kind of problem of threads interacting negatively is to create synchronized blocks rather than just methods, which we do have a synchronized method structure that we can use. We can also synchronize blocks of our code, sort of like an if statement or a try-catch, but it states this section of the code is synchronized on a particular object, meaning that if someone else tries to use that object in a synchronized block, then it will stop. So only one thread can be inside the synchronized block for a given object. We call this a monitor or a lock. We're using O to kind of lock down this section of code. Other threads are blocked. They must sit and wait until the original thread finishes the synchronized block that it's using. And so the one on the method is just shorthand for synchronizing on this object. It's synchronizing on this object and not letting other people get into those synchronized sections. When one thread exits the block, then another thread is allowed to get into that synchronized block. If several threads are waiting on the lock of a particular object, when it becomes available, one is chosen, but it's non-deterministic as to which one will be chosen. So if I have 3 threads, one of them gets into a synchronized block, then the other 2 are sitting and waiting. There is no way for me to predict which of those 2 will get access to that synchronized block next. In fact, there's no guarantee that one of them will ever get in if someone else keeps sort of jumping them in line. So there's not a good system built in for making sure that they all, for instance, wait in a queue or anything like that. It may be the case that some other thread keeps jumping in front of a thread that's waiting. And this is called a live lock, where our code is still executing, but one piece of our code is just waiting forever on a resource that it needs. We can actually use any object as the lock to synchronize on. And if we synchronize on different objects, then those are not mutually exclusive, meaning if I synchronized on object 1 here, and I synchronize on object 2 there, then two threads can execute these two separate blocks at the same time. So as long as O1, the variable used here, is not equal to O2, meaning memory equality, meaning they don't point to the same object in memory, then two threads can be running the method m here at the same time. So for instance, you might use O1 here so that you can call O1.m there, and you might use O2 here because you were calling O2.m, and that's okay, that's safe. It would not be safe if two threads tried to execute m on the same object at the same time. And so as long as the object that's being synchronized on is different, then we're allowed to do multiple threads on inside of those synchronized blocks. It doesn't even have to be a different variable. As long as you're coming in with a different instance of the object in that synchronized condition, using a different object in memory as the lock, then you're safe. You're okay to enter the synchronized block. It's when they're using the same object, like our array list before. We could have synchronized on that array list in our example and made a synchronized block on the array list, the list, before adding. And that would mean that two threads could not add to the list at the same time. And that would have solved our problem there. There is one issue that can arise from these sorts of synchronized blocks. You think about it, that threads are waiting on a synchronized block. Well, we mentioned live lock before, where one thread gets jumped in line and never gets its chance. Even if we avoid that live lock kind of condition, if we don't think about our synchronization and what we're locking on in different places of our program, then we may enter a situation called deadlock, where, for instance, thread 1 gets the lock on O1, on object 1 here, and then doesn't finish yet getting the lock on object 2, O2, and thread 2 gets the lock on O2, but then isn't able to finish getting the lock on O1 because it's already held by thread 1. Sometimes you can spot these by looking at the code, but sometimes they're not easy to spot if there are different methods that are synchronized. We may not know what their parameters are at any particular time. We may not know what order those methods are going to get called in if someone else is using our code as a library. And in particular, if there's more than two threads, the combinations of what locks they might hold at the same time can be very difficult to predict. And so we'll look at some other methods for doing this kind of ensuring thread safety with something different than locks in particular, but other ways to cause our threads to stop for a minute, think about something, wait till some condition is available, etc. But the most important lesson here is that multiple threads at once can act in conflicting ways, and one of the ways that we can address that issue is to synchronize portions of our code. That synchronizing must be done using some particular object as a lock. We usually want to aim for whatever the object is that we're concerned about being invalidated by conflicting actions between our multiple threads.